Video 5 of Chapter 9. We're going to talk about some of those errors that we mentioned toward the beginning of the chapter where we may come up with a decision in our significance test and we might be wrong. So as a result of sampling variability, there are times where we will unfortunately and unknowingly make the wrong decision with a significance test. So for instance, in the previous video, we talked about giving babies peanut butter and not peanut butter and seeing if they developed allergic reactions to peanut butter later in life as kids. And so what we found was very strong evidence. The smaller our p-value is, the stronger the evidence we have against the null hypothesis. So we absolutely kicked that null hypothesis in the rear end and said, get out of here. Peanut butter definitely does something to these kids. Whether it helped or hurt them, we didn't quite know, but it definitely makes a difference. But the thing is, we technically could be wrong here. Maybe we shouldn't have rejected the null hypothesis. So in the end, we're going to talk about the two different types of errors that we can unknowingly make. And so the first one's just called a type 1 error. And a type 1 error is when we incorrectly reject the null hypothesis, which is what we could have committed in the peanut butter problem, right? Because we rejected the null hypothesis, but maybe there's a chance that we shouldn't have rejected the null hypothesis. So in that problem, we could have made a type 1 error. Well, a type 2 error is going to be very similar. It's when we incorrectly fail to reject the null hypothesis. So notice in both type 1 and type 2 errors, we are incorrectly making a decision here. Type 1 is when we incorrectly reject the null hypothesis, and a type 2 is when we incorrectly fail to reject the null hypothesis, and we really should have rejected it in the end. Now, which error is more serious to commit? And Kevin McAllister, honestly, it just depends on the problem itself. Sometimes a type 1 error is more serious. Sometimes a type 2 error is more serious. Sometimes a type 1 error is more serious maybe for just a particular individual, and maybe a certain error is more harmful to like society in general. And it may affect more than just one person, but it honestly just comes down to the problem itself. All right, a pharmaceutical company claims that less than 10% of patients who take its new drug to treat Alzheimer's disease will experience intense nausea. So the null hypothesis is we're going to go with that we're at a 10% level here. What we want to show, what the company wants to claim is true, is really that it's less than 10%. So again, we're going to start with 10%, and then we're going to want to prove that it's really 10%. So what's a consequence of making a type 1 error? Well, we got to remember, what was a type 1 error? A type 1 error is when we incorrectly reject the null hypothesis. So we have to reject the null hypothesis. So we reject the null hypothesis. We think this is the truth, but we incorrectly do that. So we think that the proportion is actually less than 10%, when in fact it's actually 10% or potentially more than 10%, right? So a consequence of making a type 1 error is we think that this medication is going to do good to patients who have Alzheimer's disease, and they will not experience as much intense nausea as what they maybe once did. So the consequence is we're going to give these people this pill. So patients will receive the medication, but unfortunately, more of them will experience intense nausea. Not a great thing for your patients, right? They're not going to be happy. There could be lawsuits that come about this. We don't know, but it's not a good thing. We say it's less than 10% when in fact it's really not less than 10%. And it's kind of like false advertisement, think of it that way. Now, a consequence of a type 2 error. Well, a type 2 error is when we incorrectly fail to reject the null hypothesis, right? So we are not going to reject the null hypothesis. We're going to say it's at 10%, but really we should have rejected it. We should have went with the alternate. So what does that really mean in this particular scenario? So we think patients are going to experience intense nausea, when in reality, fewer patients will experience intense nausea. So we believe patients will experience more cases of intense nausea than what will really occur. Now, if that's the case here, the pharmaceutical company may decide to not sell this particular medication. And so, they may take it off the market when, in fact, it really could help these Alzheimer's patients. They won't experience as much intense nausea as what we thought maybe they would have experienced if we had given it to them. So, in the end, which one is really the worst one? I'd almost say a type 1 error, right? We're giving these patients medication that's making them feel very nauseous. When in the other case, I don't know. I could see some people going, I think a type 2 error is worse because we're not giving them the medication that they could use so they don't feel as nauseous. So sometimes it's a toss-up about which one's really the more serious one to commit here. Now, what is the probability of a type 1 error? And so in order for us to make a type 1 error, we first need to reject the null hypothesis. And when we reject the null hypothesis, that must have meant that our p-value was smaller than our alpha or significance level. And so really, the probability of a type 1 error is whatever the significance level is. And a type 1 error we can call basically a false positive. We reject the null hypothesis. That's typically the positive thing that we want to do here, but it was a false result. We really shouldn't have rejected the null hypothesis. Now you might be wondering, why exactly is a type 1 error just the alpha level? So I got a picture here that I want to show you. So there is a sampling distribution that really represents the null hypothesis. And so the null hypothesis, we're saying that the center, whatever that value is true. So we're always assuming that the null hypothesis is true to start with. And so when are we going to reject the null hypothesis? And that's when we have a p-value that is smaller than the alpha level. So let's say the alpha level's right here, whether that's 5%, 1%, 10%, I don't know. Whatever the alpha level is right here, if we ever get results that are smaller than that alpha level, then we would reject the null hypothesis. So it's in all of these scenarios down here that we would even reject the null hypothesis. And so remember, a type 1 error is when we reject the null hypothesis, but we shouldn't have. But the first thing we got to do is reject the null hypothesis. So whatever that alpha level is, all these percentage of p-values, which would be that alpha level, would be the probability of making a type 1 error. Now, what does the rest of the distribution represent, right? If we assume that the null hypothesis is true and we fail to reject the null hypothesis, well, that's really a true negative. That would be 1 minus alpha. And so failing to reject the null hypothesis, and it's the correct decision to make in the end. That's what the rest of this 1 minus alpha really represents. A common misconception that sometimes people think of is that a type 1 error and a type 2 error are really just the opposite of each other. But you got to consider they're both errors, so the opposite of one error can't still be an error. The opposite of an error has to be a correct decision, right? So if this down here represents a type 1 error, then all the rest of this distribution has to represent making not an error. So we fail to reject the null hypothesis, and it has to be the correct decision to make in the end. So what about a type 2 error? What is the probability of it? And I want to tell you, a type 2 error probability gets to be a little bit more complicated. And the main reason for that is the alternate hypothesis, it is not a fixed value, right? The null hypothesis is a fixed value. We're saying that p equals some particular value, and it doesn't move around. The alternate hypothesis, on the other hand, is some sort of inequality, right? Typically we say P is less than, P is greater than, but we don't give it a specific value that it must be specifically less than the null hypothesis, for instance. So the problem is the alternate hypothesis distribution. It's kind of a shifting thing. So a type 2 error really depends on a specific value for the alternate hypothesis. The closer the alternate hypothesis value is to the null hypothesis, well, we're not going to make a type 2 error as often. But the further away that our alternate hypothesis value is from our null hypothesis, the lesser chance that we have of making a type 2 error. So in the end, what I need you to know is this. You do not need to worry about how to calculate a type 2 error in AP statistics. You absolutely do not need to know that. And the probability of making a type 2 error is just going to be the Greek letter beta. We're just going to call it beta. You do not need to worry how to calculate beta. Once upon a time, there was a free response question, and it was the investigative task question, question 6. And unknowingly to me, as I was working through the problem, all of a sudden I realized I was calculating step by step by step. I was calculating what a type 2 error was, and I couldn't believe that that's what I was really doing. I had never really considered that before. So even though it's been asked technically on an AP exam, it was the investigative task question, which is more of a think outside the box type of problem. I would not worry about how you actually come up with this number. Now, a type 2 error is referred to as a false negative. So we call it a negative because we failed to reject, but again, it's false because it's the error component here. We really should have rejected the null hypothesis. Now, the opposite of a type 2 error is when we reject the null hypothesis and it is the correct decision to make, which ultimately means that is a true positive. When we reject the null hypothesis, that is a positive result, and it's the correct decision. It is a true decision to make. Now, a true positive is what I would say is the ultimate goal of a hypothesis or a significance test. And here's the great thing. It has a special statistical name. So when we correctly reject the null hypothesis, it is called, let me space that out a little, it is called power. So power is the complement of a type 2 error. A type 2 error plus power will equal 100%. So if you know one of those probabilities, you can switch it around and figure out what the other probability is. So again, type 2 error and power are complements of each other. So there are 3 ways that we can increase power to correctly reject the null hypothesis. We can, number 1, increase the sample size that we used in our sample. What this will do is it'll decrease the standard error, that square root part of our standardized test statistic, and therefore making it easier to reject the null hypothesis. And I will say this is the ideal way to increase power out of the 3 ways that we're going to discuss. Just increase your sample size. The second way is what I would like to call the cheater's way, is to increase your alpha level, right? So think about this. If we increase the alpha level, that means that there are more p-values that would exist that would allow us to reject the null hypothesis. So if you think about, like, what if our p-value was, 0.07 and we used an alpha level of 0.05? Well, the p-value is not less than alpha, so we fail to reject. But what if we said the alpha level was really 10% instead? Well, now 7% is less than 10%. Now we get to reject the null hypothesis. But do you see how that's kind of like cheating? Like, whatever the p-value is, you can always make the alpha level greater than it so that you're naturally going to reject the null hypothesis. So again, I would call this the cheater's way of increasing power. The third, which we're not really going to discuss too much about here, is to increase the distance away from the null hypothesis. The further away our alternate value is, away from the null hypothesis value, the easier it will be to reject the null hypothesis. And again, this kind of goes back to whenever I was showing you, let me jump back to here. So this would be like the alternate hypothesis value. The closer it is to the null value, the harder it will be to reject the null hypothesis, because what we are hypothesizing for and what we're hypothesizing against, there's not much difference between them. So it's really going to be hard to reject something when our alternate is so close to that null hypothesis value. But if the alternate value is further and further and further away from our null hypothesis value, it starts to become very, very easy to reject the null hypothesis in that situation. So again, don't worry too much about this third way. I'd say the main way you need to remember is just increase our sample size. We could increase the alpha level, but again, that's kind of like cheating. All right, let's take a look at an example before we end out the video here. A local high school makes a change that should improve student satisfaction with parking at school. Before the change, 37% of students were satisfied. A random sample of students were surveyed 1 month after the changes, which found 42% were satisfied. A significance test is carried out at the alpha equals 0.05 level to determine if the increase is statistically significant. So number one, what is the probability that we make a type 1 error? Well, the probability of a type 1 error was just the alpha level, which was given to us as 5%. Type 1 error is always going to be super easy to calculate because you have to have an alpha level to consider to do your hypothesis test with. Now, the test has a power of 75% to detect that P is really 0.45. Now, before we explain what this fully means here, I want you to consider that the null hypothesis in the end, or really at the beginning of the problem, was that the satisfaction rate was 37%. We're going to pretend like whatever changes they made didn't make a difference, that it's still the same satisfaction rate. Versus they make some changes that they're hoping will increase the satisfaction rate, right? So consider that the alternate hypothesis is a number that's bigger than 37%. We're hoping that we increase the satisfaction rate. But really, what value could P represent? That would be greater than 37%. Well, 38% is greater than 37%. 39% is greater than 37%. 54% is greater than 37%. There's a lot of different values that P could be that would be greater than 37%. So the power of the test, the probability of that power, is going to fluctuate depending on what that value of P is for the alternate hypothesis. And again, that third way that we can increase power is to get further and further away from the null hypothesis value. So this is saying right now that if P was really 45%, then there's a 75% chance that we will correctly reject the null hypothesis. How do I make this 75% go up even higher? I would need to make this 45% get even bigger so that it's further away from the 37%. That's really what that third way means. All right, so now let's talk about, and I did really just kind of mention what that 75% power really means here. So there is a 75% chance. I mean, really, that's what power is. It's a probability value. There's a 75% chance that we correctly reject P equals 0.37 in favor of, now we're in favoring of something greater than 37%, but they gave us a specific number to be in favor of for the alternate hypothesis. So in favor of a proportion of 45%. So again, power is the probability that we correctly reject the null hypothesis in favor of, and they typically have to give us a specific number to be in favor of in that instance. Hold up. Now, you are being asked to figure out what is the probability of committing a type 2 error. And I want you to remember there was a special relationship between the power probability and the type 2 error probability. So that is for you to do. And then I want to finish us off with this is that this is really a summary of all the situations that really could occur. And so 2 of them are good things and 2 of them are bad things. We got our 2 errors and not our 2 errors. So if the null hypothesis is actually true, but we reject it, that was a type 1 error. That was a false positive, and it has a probability of alpha. But what if the null hypothesis is really true and we don't reject it? Well, if it's really true, we shouldn't reject it. So that would be a correct decision to make, and it's really having a true negative result. And that's what is the opposite of our type 1 error. So what people will commonly mistake is they think that all 4 of these situations in this table must represent 100%. But there's really 2 alternate situations that are happening. The null hypothesis is either actually true or it's actually false. So if it's actually true, we might be making the correct decision or the wrong decision. And so these 2 things have to add up to be 100%. Or if the null hypothesis is actually false, then we are either going to make the wrong decision or the right decision regarding the null hypothesis. And so again, these 2 things have to add up to be 100% as well. Now, in the end, I will say 3 out of these 4 things we made a big deal about in this video, right? We had type 1 errors. They had a special probability. Type 2 error had a special probability that we said we don't have to worry about how we got that, but you'll be able to figure it out based on the information given to you. And a true positive was power, and that was the probability of 1 minus our beta probability. So that was a great thing. The one thing we just kind of gloss over and ignore is a true negative result. So it doesn't really have a special name that I know of, but I just want you to know we don't really discuss true negative situations, ultimately because we're trying to reject the null hypothesis. And in this scenario, we're holding on to it. We're not saying it's true, but we just don't have enough evidence to prove that it's not true. All right, so go back to your you-do problem, figure out real quick what that type 2 error is, and we will discuss it the next day in class.